So we need to determine the convergence or divergence of the following series. So let's just say we think it's divergent, and we would like to compare it to, say, 1 over n. Then in that case, we would want to show that 1 over ln of n squared is greater than 1 over n. If we can show that, we're in great shape. Well, to show that, we would need to show that n is greater than ln of n squared. So basically, we're asking this question right now. That's what we need to show in order to get what we want to show. Well, let's find out. To find out which one's greater, what we can do is we can do the limit as n approaches infinity of the ratio of the two. So since we want to show n is bigger, let's put it on bottom. So ln of n squared. This is a very useful aspect of limits and proofs. Basically, if n is larger, this limit should be 0. So if I can show this limit's 0, I've got the hypothesis I need in order to get the conclusion I want. So this is an infinity over infinity case, which allows me to use L'Hopital's rule. So the derivative on top, and then we'll recalculate the limit, is 2 times the natural log of n times 1 over n. And the limit on bottom is just 1. So let's rewrite what we have here. Limit as n goes to infinity of 2 ln of n over n. Once again, we have an infinity over infinity case, so I can actually use L'Hopital's again. So now when we use L'Hopital's, this is just going to be 2 times 1 over n over 1. Simplifying what we have, we've got the limit as n goes to infinity of 2 over n when all said and done. We know that that limit is equal to 0. So what we've done is we've shown that n is in fact larger than ln of n squared. So we no longer need this piece, which means this 1 over ln of n, the quantity squared, is greater than 1 over n. So this guy is going to diverge by our comparison test. In fact, what we're comparing it to is our harmonic series of 1 over n, which we know is divergent by p-series. So this is a nice use of limits if you need to show that something is greater than something else.